Welcome! In this session, we will tackle problem number 1081, titled Smallest Subsequence of Distinct Characters. We'll explore the problem requirements, break it down step by step, and analyze the most efficient solution. Let's dive in. In this problem, the task is to find the smallest subsequence of a given string S that includes all the distinct characters in S exactly once. Additionally, the subsequence must be in lexicographical order, which means the characters should appear in the same order as they would in a dictionary. A subsequence, as a reminder, is formed by deleting 0 or more characters from a string without rearranging the order of the remaining characters. For example, in the string ABC, AC is a valid subsequence, but CA is not, because the order of the characters cannot change. The input to this problem is a string S of lowercase English letters, with a length between 1 and 10,000. The output is a string representing the smallest subsequence that meets the criteria. Let's now look at some examples to better understand the problem. Consider the first example, where the input string is S equals cap. The distinct characters found in this string are B, C, and A. To form the smallest subsequence containing all these characters exactly once and in lexicographical order, we arrange them as ABC. This is because among all possible subsequences that include these three characters, ABC comes first in dictionary order. This gives us our output, ABC. In the second example, the input string is S equals back. The distinct characters here are C, B, A, and D. To form the smallest subsequence in lexicographical order, we select ACTB. This is the result because it maintains the correct order of the distinct characters, while respecting the dictionary order among possible valid subsequences. For instance, ABCD would not work, as it does not preserve the order of characters as they appear in the input string. Now, in the third example, the input string is S equals ZXYZX. The distinct characters in this string are Z, X, and Y. To determine the lexicographically smallest subsequence, we arrange them as XYZ. This sequence not only includes all the distinct characters, but it also respects the order in which they must appear to maintain the desired properties. Hence, the output is XYZ. Finally, let's consider some edge cases. For example, if the input string is a single character, like S equals A, the result is simply the string itself, as there's only one distinct character. If all characters in the string are already distinct, such as S equals ABCDEF, the result is again the string itself, since it's already in lexicographical order. On the other hand, if all characters are identical, such as S equals AAAA, the output is just A, as it's the only distinct character. For a more complex case, where characters are repeated and unordered, like S equals CAC, the result is ABC. This ensures that the smallest lexicographical sequence with distinct characters is chosen while following the rules of subsequences. When tackling the problem of finding the smallest subsequence of distinct characters, the brute force approach provides an intuitive starting point. The idea here is to generate all possible subsequences of the input string S, and then filter those subsequences to include only the ones that contain all unique characters exactly once. From this filtered set, we select the lexicographically smallest option. To break it down, we first generate all subsequences, which is a computationally expensive operation with an exponential time complexity of O2 to the power of n. Then, for each subsequence, we check if it satisfies the uniqueness condition, adding another O(n) per subsequence. Finally, we compare valid subsequences to find the smallest one lexicographically. While conceptually straightforward, the total complexity of O2 to the power of n*n makes this approach impractical for large inputs. The trade-off here is clear: it's simple to implement but infeasible due to its exponential runtime. To address the limitations of the brute force method, an optimized approach using a greedy algorithm with a stack emerges as more efficient. The intuition behind this method is to iteratively build the smallest subsequence while ensuring that distinct characters are included. A key observation is that we can use a stack to construct the result incrementally, while also leveraging two auxiliary structures to assist in decision-making. First, the last_occurrence map keeps track of the last index where each character appears in the string, ensuring we know whether a character can still appear later. Second, an in_stack set allows us to quickly check if a character is already in the stack. At each step, we traverse the string character by character. If the current character is already in the stack, we skip it. Otherwise, we pop characters from the stack if the current character is smaller than the stack's top element and the top character can still appear later. Once this condition is satisfied, we add the current character to the stack and mark it as present. This ensures that the result is both valid and lexicographically smallest. The efficiency of this greedy algorithm comes from its use of linear traversal and stack operations that are amortized O(1) per character. This results in a total time complexity of O(n), making it highly efficient for large inputs. While this approach is elegant and efficient, it does require careful implementation to manage the auxiliary structures and ensure correctness. Another alternative approach worth mentioning is sorting the characters of the string and constructing the subsequence greedily from the sorted result. Here, we sort the string, traverse the sorted array, and add characters to the result if they are not already included. This method is simpler than the stack-based approach but less optimal due to the sorting step, which has a time complexity of O(n) log n. While it avoids the exponential runtime of the brute force method, it still falls short in efficiency compared to the greedy stack approach, which achieves O(n). The chosen strategy for this problem is the greedy algorithm with a stack, as it strikes the perfect balance between efficiency and correctness. The breakthrough insight here was recognizing that we could reduce the problem to a stack-based approach by leveraging the properties of lexicographical order and the uniqueness constraint. Using the last underscore occurrence map, we dynamically ensure that removing a character from the stack is safe, while the in underscore stack set prevents duplicates. This guarantees that the resulting subsequence is both valid and lexicographically smallest. Compared to alternatives, this approach stands out for its O(n) runtime, making it highly scalable for large inputs. While the brute force method is conceptually simple, its exponential complexity renders it impractical, and the sorting-based method, though easier to implement, is less optimal. By combining efficiency, clarity, and correctness, the greedy stack algorithm is undeniably the best fit for solving this problem effectively. The problem we're tackling involves finding the lexicographically smallest subsequence of a string such that every distinct character appears exactly once. To solve this, we start by determining the frequency of each character in the string. This is done by traversing the string and counting occurrences of each character, storing these counts in a hash map. For instance, if the input string is kbak, the frequency map becomes C4, B2, A1, D1. This map is crucial because it allows us to track how many instances of each character remain as we process the string. Next, we initialize two data structures, a stack and a visited set. The stack is used to build the result incrementally, ensuring characters are added in order, while the visited set helps us avoid adding duplicate characters to the stack. Initially, both the stack and the visited set are empty, and this setup creates the foundation for our solution. Now, we iterate over each character in the string. For every character ch, we first decrease its frequency in the frequency map, since it is now being processed. If the character is already in the visited set, we skip it to ensure it doesn't appear more than once in the result. When adding a new character, we check if the top character in the stack is lexicographically larger than the current character and if it still has remaining occurrences in the string. If both conditions are met, we remove the top character from the stack and the visited set. This ensures that the result remains lexicographically smallest. Once these checks are complete, the current character ch is added to the stack, and it is marked as visited. Finally, to generate the result, we simply concatenate the characters in the stack. For example, if the stack contains A, C, D, B at the end of the iteration, the resulting string will be ACB. Several key insights make this algorithm work efficiently. First, by maintaining lexicographical order during the stack operations, we ensure the smallest possible result. The visited set plays a critical role in avoiding duplicate characters, which maintains the exactly once condition required by the problem. The frequency map helps us keep track of how many instances of each character remain, ensuring we make informed decisions when modifying the stack. The algorithm relies on three main data structures: a hash map for the frequency count, a stack to build the result, and a set to track visited characters. In terms of complexity, the time complexity is O(n), where n is the length of the string, since each character is pushed and popped from the stack at most once. The space complexity is O(n), which accounts for the hash map and the stack, making this approach both time and space efficient. To see the algorithm in action, let's walk through an example with the input string back. First, we calculate the frequency map C4, B2, A1, D1. We initialize the stack as empty and the visited set is empty. Starting the iteration, the first character C is added to the stack, so the stack becomes C, and the visited set is C. Next, B is added, resulting in C, B, and C, B. When we encounter A, we remove B and C from the stack because they are lexicographically larger and still have remaining occurrences. This leaves the stack as A, and the visited set is A. Then C is added back, making the stack A, C, and the visited set A, C. Next, D is added, resulting in A, C, D, and A, C, D. The next C is skipped because it's already visited. Then B is added, making the stack A, C, D, B, and the visited set A, C, D, B. Finally, the last C is skipped as well. The stack at the end is A, C, D, B, and the resulting string is ACP. Here, we start by defining our function's smallest subsequence, which takes a string S as input. The goal is to determine the smallest subsequence of distinct characters from the string while maintaining their original order. To achieve this, the first step is to count the frequency of each character in the string. We use a dictionary called char_count where each character in S becomes a key, and its frequency is the corresponding value. This will help us keep track of how many times each character appears as we process the string. Next, we initialize a stack to build our result incrementally and a set called visited to track which characters are already added to the stack. Both of these will help ensure that the resulting subsequence is both lexicographically smallest and contains distinct characters. Now, as we iterate through the string, we first decrement the frequency of the current character in char_count since we've encountered it. If the current character is already in visited, we skip it to avoid duplicates. Otherwise, we enter a loop where we check if the top character in the stack is lexicographically greater than the current character and still appears later in the string, based on its frequency in char_count. If both conditions are met, we remove the top character from the stack and also from the visited set, making room for the current character to take its place. After ensuring that the stack only contains the characters that are necessary and in the correct order, we add the current character to the stack and mark it as visited by including it in the visited set. This guarantees that each character is added to the stack at most once, maintaining its distinctness in the result. Finally, once all characters in the string have been processed, the stack contains the smallest subsequence of distinct characters in the correct order. To return the result, we simply join the characters in the stack into a single string using the join method. This effectively converts the stack into our desired result, which meets the problem's requirements. Here, we start by defining the smallest subsequence method, which takes a string S as input. The first step is to count the frequency of each character in the string. To accomplish this, we use a hash map called charCount, where each character is stored as a key, and its frequency as the value. We populate this map by iterating through the string and updating the counts using the getOrDefault method. Next, we initialize a stack to help construct the result and a hash set called visited to keep track of characters that are already part of the result. Now, as we iterate through the string again, we first decrement the frequency of the current character in charCount since we are processing it. If the character is already in the visited set, we skip it because we do not want duplicates in the result. Otherwise, we consider whether to remove characters from the stack. Specifically, we check if the character on top of the stack is lexicographically greater than the current character and if it still appears later in the string, as indicated by its frequency being greater than 0. When this condition is true, we remove the top character from the stack and also remove it from the visited set, ensuring that it can be added back later if needed. Once we finish adjusting the stack, we push the current character onto the stack and mark it as visited by adding it to the visited set. After iterating through all the characters in the string, we move to constructing the final result. To do this, we initialize a string builder and repeatedly pop characters from the stack, inserting them at the beginning of the string builder. This ensures that the characters are in the correct order, as the stack naturally maintains the reverse order of insertion. Finally, we return the resulting string built from the string builder, which is the smallest subsequence of distinct characters in lexicographical order. Let's continue. Let's continue. Let's continue. Let's continue. The time complexity of this solution can be understood by analyzing each step. First, in step 1, we count the frequency of each character in the string. This requires iterating through the string once, so it takes n time, where n is the length of the string. Next, in step 3, we process each character during a second iteration. Each character is added to the stack and the visited set at most once. The while loop inside this step may remove characters from the stack, but since each character can only be added and removed once, the total number of stack operations remains n. Therefore, the time complexity for this step is also n. These two steps dominate the overall process in terms of time complexity. In step 4, the final conversion of the stack into a string involves concatenating the characters in the stack. This operation takes k time, where k is the size of the stack. Since the stack contains at most one occurrence of each distinct character in the string, and there are only 26 lowercase English letters, k is at most 26. This makes the conversion step effectively 1. Combining all steps, we have n for counting frequencies, n for processing characters, and 1 for the final conversion. Adding these together, the total time complexity is n. Now, turning to space complexity, we start with the frequency dictionary, which stores counts for at most 26 characters. Since this is bounded by a constant, its space usage is 1. The stack, used to store a subset of distinct characters, also has a maximum size of 26, as there are at most 26 distinct lowercase letters. This means the stack contributes 1 to space complexity. Similarly, the visited set, which keeps track of characters already in the stack, is limited to 26 entries, so its space usage is also 1. The input string itself, however, requires n space because its size grows with the length of the input. Therefore, the overall space complexity is dominated by the input string, resulting in n total space usage. To understand why this approach is efficient, compare it to a brute force solution. In a brute force approach, we would generate all possible subsequences of the string, check which ones contain distinct characters, and then determine the lexicographically smallest subsequence. Generating all subsequences has a time complexity of 2 to the power of n, with even more time required for filtering and sorting. This is clearly infeasible for large inputs. In contrast, the current solution uses a greedy algorithm combined with stack-based processing, ensuring each character is handled exactly once. This brings the time complexity down to n. The auxiliary data structures, which are bounded by the size of the alphabet, ensure that space usage beyond the input string remains constant. This makes the solution both time efficient and space efficient. Analyzing the best, average, and worst cases, we find that the time complexity remains n across all scenarios. In the best case, such as when the input string already contains distinct characters in lexicographical order, we simply iterate through the string without needing to pop any elements from the stack. In the average case, each character is pushed and popped from the stack at most once, maintaining linear complexity. Even in the worst case, like with a reverse-ordered string such as ECBA, where characters are pushed and popped frequently, each character is still processed no more than twice. This ensures the overall complexity remains n. Mathematically, since each character is processed exactly once and each operation on the stack is bounded, the solution guarantees linear time complexity. The constant space usage for auxiliary structures further supports the efficiency of this approach. When solving this problem, there are several common mistakes to watch out for. First, overlooking edge cases can lead to incorrect solutions. For example, consider edge cases like empty strings, strings where all characters are identical, or very short strings with only one or two characters. These scenarios often reveal flaws in algorithms that assume strings are diverse or of significant length, so it's important to test these explicitly. Another common pitfall is relying on inefficient brute force approaches, such as generating all possible subsequences of a string. This is unnecessary because the problem only asks for the smallest lexicographical subsequence of distinct characters. Brute force methods might work for small inputs, but their exponential growth makes them impractical for larger strings. Instead, optimized techniques like using a greedy algorithm or a monotonic stack are much more efficient. Lastly, mishandling lexicographical order is a frequent issue. For instance, when removing characters from a stack, failure to ensure the smallest lexicographical order results in incorrect solutions. By tracking the last occurrence of each character and carefully managing the stack, you can avoid these mistakes and ensure the correct result. Another mistake to avoid is skipping character frequency tracking. Without a frequency counter, it's easy to remove a character from the result prematurely, which could make it impossible to construct the desired subsequence later. By maintaining a frequency map, you can ensure that each character is processed correctly. Similarly, it's important to be mindful of space usage. Using additional data structures unnecessarily, such as storing all possible subsequences, leads to inefficient solutions. This is particularly problematic for larger inputs, where memory usage can become a bottleneck. Instead, aim for simpler implementations that rely on a single stack and a set, which are both space-efficient and effective for this problem. Keeping these optimizations in mind will help you write both correct and efficient code. When tackling problems like this in interviews, there are a few key insights to keep in mind. First, many problems involving lexicographical order and unique subsequences follow a similar pattern. They often require a greedy algorithm combined with auxiliary structures like stacks and sets. This makes recognizing the pattern crucial. Additionally, always clarify the problem requirements up front. For example, confirm whether duplicates are allowed, whether the order of characters matters, or if you need the smallest lexicographical result. Starting with a brute force solution can help you understand the problem, but it's important to optimize iteratively by identifying redundant steps or bottlenecks. Interviewers may also ask follow-up questions, such as how to optimize space usage or handle extended character sets like Unicode instead of ASCII. Related problems include LeetCode 3.16, remove duplicate letters, which also uses a stack and frequency map to maintain lexicographical order, and LeetCode 4.02, remove k-digits, which applies similar principles to numbers rather than characters. Other related problems include LeetCode 1081, the smallest subsequence of distinct characters, which is directly tied to this problem and operates under similar constraints. Another useful problem to study is LeetCode 946, validate stack sequences, which tests a deep understanding of stack mechanics and can help build intuition for solving stack-based problems. When considering alternative approaches, sorting and filtering the string is one option, but this breaks the original order and is invalid when order preservation is required. Dynamic programming is another approach, where you find the smallest subsequence using DP techniques. However, this is often overkill for problems that can be solved with more straightforward greedy algorithms. The most widely recommended method is to use a monotonic stack combined with hash maps to track the last occurrences of characters. This approach effectively balances time and space efficiency and is considered optimal for solving these types of problems. Great job! To recap, we solved the problem using an efficient stack-based approach coupled with hash maps. Remember, mastering foundational data structures is key to solving problems like these efficiently. Thank you for watching, and don't forget to like, subscribe, and stay tuned for more coding solutions. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!